Good afternoon, everybody. Thanks for coming. Welcome to the session on operationalizing Snowpark Python. My name is Caleb Bechtold. I'm one of our field CTOs for machine learning and AI here at Snowflake. If you haven't worked with my team or some of our counterparts, probably thinking like, what the heck does field CTO do? Seems like a pretty weird job title. I thought the same thing when I took this job. So loosely, what our team does is we're really the tip of the spear for all things machine learning and AI and data science for customers, partners like yourselves. Another kind of team of ML architects and engineers just here to be deep technical, subject matter experts and resources to help our customers, get enabled on using Snowflake for machine learning and AI. Now, if you're not a machine learning engineer or data science practitioner, have no fear. This session really has nothing to do with data science. An artifact of our team being engineers who've worked predominantly in Python to do data science, that we were the de facto team for all things Snowpark Python when it got released out into the wild, either on purpose or on accident. I'm not exactly sure. But it's been really cool to get to see over the last really 18 months or so, where customers from early private preview all the way through GA releases of Snowpark Python last year are doing some really impressive and powerful things with Snowpark Python on Snowflake. Before we get started, I have one apology to make. The first is that if you came to the theater session I did on this yesterday, it was a condensed version of largely the same talks. There's going to be some repeat content there. The second is that I've been doing a lot of talking the past 2 or 3 days, so if you've had to already listen to me, sorry, this is what you get. And the third thing is just that while I will attempt not to do this, there's no demo portion today, but we will try not to do full death by PowerPoint for the next 45 minutes, and hopefully we'll keep things interesting. I'm going to require a little bit of participation before I get started though. How many of you here have experimented or tried out Snowpark Python already? Okay, great. How many of you have production workloads that are running using Snowpark Python? Fewer. Okay, cool. That's very helpful. So we're going to walk through basically over the course of the next 45 minutes, a little bit of a refresher on just what Snowpark Python even is. What is Snowpark is both my favorite and least favorite question that customers ask me on a regular basis, because it's kind of a hard one to answer, honestly. We'll talk a little bit about how to build a mental model for using Snowpark Python components and sort of how those different usage contexts work together, how they execute, how they actually work on the back end. Kind of take a look at a quick example workflow, how you might actually build a pipeline using Snowpark components, how I personally would think about organizing and structuring and architecting that code, designing that workflow. We'll talk a little bit of DevOps and MLOps. This will be the only portion where we really kind of touch on some data science components, because now when you start talking Python code in, at that kind of the most kind of simple level in database execution, you're starting to introduce and overlap data ops, database management, traditional software DevOps, CI/CD. There's a lot of complexity associated with that. So we'll touch on that a little bit. And then I'll go through what I teased yesterday, which is my 10 commandments for performance design with Snowpark Python. One thing that I think has been really interesting to observe over the last 18 months or so is that oftentimes we come to customers talking about Snowpark Python, and there's really 3 kind of main persona groups that most of the technical folks that I talk with on a daily basis fall into. The first is the SQL power user, very comfortable with Snowflake, understands how virtual warehouse compute works and all of our scaling capabilities and micro-partition data storage, things like that. But in a SQL context, they're accustomed to writing SQL stored procedures, SQL scripting, SQL UDTFs, obviously far more adept at writing SQL queries than I am. The extent to my SQL knowledge is select star from table, basically. That's what we do in data science. We select star from table. We pull it somewhere else. Somebody in IT gets really pissed off at us. That's the data science world. So you have that person for whom Snowpark Python is largely just about understanding what the open source community around Python now it provides to them in terms of extending functional capability to do workloads at scale on Snowflake, right? A lot of the compute primitive concepts that we'll talk about are familiar to this person, and we're really thinking language specific, kind of new material, and then ultimately some of those DevOps, CI/CD sort of concepts that I mentioned before. The second is the Spark user. The Spark user, I think, is probably the most familiar with the Snowpark Python concepts as they get started. Predominantly what we're talking about there and the challenges that we see are just really understanding some of the nuances in terms of how the backend execution actually works, how you think about managing compute resources in Snowflake compared to Spark, wherever that may be running, all those kinds of things. But largely the concepts of the DataFrame API and distributed compute and UDF execution and pandas UDFs or user-defined table functions or whatever it may be. These are familiar concepts, at least, and we're really just talking about the nuances and differences between the two execution frameworks. And then the third persona is the Python user, the pure vanilla Python developer, whether you're a software engineer, a data scientist, whatever it may be, who's accustomed to working in single node Python sort of environments, locally on cloud VMs, but not really thinking about Python at scale, right? So this person's very familiar with all the libraries and the functional kind of capabilities with developing in Python. They know pandas. We all love pandas, right? But this concept of large scale data processing is often kind of where this person's unfamiliar. And in particular, the notion of packaging and bundling and deploying Python code as seemingly in database kind of objects and structures and things like that is a pretty foreign concept. So how many of you, show of hands, would say you fit Persona 1, SQL Power user, opening up the world of Python? Okay, great. What about Persona 2, Spark user? Okay. And number 3, Python developer. All right, it's a pretty good healthy mix here. So this will be fun. Either we'll get something valuable for everyone or everybody's going to leave disappointed. One of the two, I don't know. All right, let's just jump in. So when we're talking about Snowpark Python specifically, and this notion of what is Snowpark has just gotten increasingly complex as we've introduced like Snowpark ML, Snowpark Model Registry, Snowpark Container Services. It's like, what the heck is Snowpark actually? When I'm talking Snowpark Python, I'm really talking about two distinct but related components. The first are our user-facing client-side APIs. In the case of Python specifically, this is a PySpark-like DataFrame API, giving you DataFrame-style syntax through a client library that you can pip install anywhere that you can run Python and ultimately connect to Snowflake and perform 100% compute pushdown for DataFrame style transformations on that data. Again, for the Spark user, you're like, yep, cool, got it. There's data. I have a data frame that references that data. When I do these transforms, they lazily execute on my compute, and then I have results. Cool. SQL user is like, wait, you're telling me that these are basically just doing SQL queries and they're using the exact same compute? You got it. That's exactly right. And then the Python user, this is where it gets a little different if you're accustomed to in-memory, eager execution of pandas data frames. But that's the core concept, right? It is for non-SQL client libraries that give users either a more friendly, more familiar, or easier to use in the case of integrating with existing, non-SQL sorts of applications, friendly APIs to start manipulating data in Snowflake, transforming it, producing analytic results, so on and so forth, without having to extract the data. The second part that I think gets really confusing as we talk about designing applications to use Snowpark Python is the server-side components. These are the user-defined functions, table functions, stored procedures, et cetera, that give you a Python runtime executing inside of Snowflake on Snowflake Virtual Warehouse compute resources, parallelizing and distributing that work oftentimes automatically for you when you write these. But it's this notion of taking functional bits of code that process data in some fashion and deploying those to execute on compute resources that may be different from the place where you built and developed them. This is, it gets where especially tricky, I think, for the pure kind of Python developer and engineer. But fundamentally, these server-side components are really what is enabling new types of data engineering and data science, data application workloads on Snowflake through this ability to deploy arbitrary code in various languages. Obviously, we'll focus on Python today because, again, as a data scientist, that's really the only thing I'm good for, but really including Java and JavaScript as well, and opening up this execution engine and the same kind of scalability, performance, governance, and security that you're accustomed to with SQL on Snowflake, opening that up to non-SQL workloads. Largely where we've seen Snowpark adoption since the early first releases all the way through general availability announcements last November are through traditional kind of data transformation pipelines, batch scoring for model inference in the case of machine learning and AI, ML training in some kind of specific cases, and eliminating the need for complex intermediary services for data applications. Fundamentally, really, the goal here is that you get to focus on just writing code and not thinking about how to scale that code. But in order to really take advantage of that, we have to understand these core kind of Snowpark Python concepts that ultimately accelerate and streamline that development process and simplify your overall software design and technology infrastructure and data architecture. Just some simple examples of those two components and a little bit about how they work. We'll get into a lot more detail, especially on the Python function side of things. In the client API, as I mentioned, has the DataFrame syntax, which you can see an example along the top there of doing a filter type operation against some data in Snowflake. Fundamentally, when you trigger execution of DataFrame API code, it's lazily executed. So it's only triggered when by some sort of collect or write type operation that actually forces the transforms to build. What we do on our side is generate optimized SQL that maps to the corresponding DataFrame transforms you've built up. Push that SQL down to Snowflake, and it runs on the Snowflake Virtual Warehouse SQL execution engine the same way it would if you just wrote native SQL. So you get 100% native SQL performance on Snowflake using the DataFrame API. When we talk about performance considerations, that's something important to keep in mind. Even though you're writing Python DataFrame code, no Python code actually executes on Snowflake, right? The result of that is you get kind of the most optimized runtime and performance for that transformation on the Snowflake compute resources. Server-side functions do execute as Python code, whether those are user-defined functions or stored procedures. We'll talk about the difference in a minute. They actually execute on in a Python runtime in a sandboxed environment on the compute nodes that comprise the virtual warehouse. In Snowflake, different sizes of virtual warehouses have different numbers of compute nodes associated with them. Larger warehouses have more. Essentially what we do is we take your Python functional code, and whether you author it outside of Snowflake and then push it to us or directly inside of Snowflake, doesn't really matter. We essentially serialize that Python code to bytecode, push it to Snowflake, and then configure a function to load that bytecode into a Python runtime that we then host for you and execute it. Snowflake then also, of course, in the context of a function where you're passing data into the Python runtime as well, handles like the distribution and routing and parallelism of that execution, which we'll get into in more detail here. And I would be remiss not to mention, as part of that, of course, the large reason for Python adoption has to do with the robustness of the open source ecosystem. We provide out of the box, through a partnership with Anaconda, hundreds, thousands of out of the box common packages and libraries that you would expect in that runtime, so that if you're writing functional code that depends on NLTK to do some sort of unstructured text processing or something like that, you don't have to worry about bundling that up either. It's just all there for you. There's really three kind of core principles along the top to be aware of. Client API, which I think I've probably talked enough about here. The UDFs, or user-defined functions, which are data in, data out, right? Data processing, custom sort of functional processing. Again, if you're used to SQL UDFs, should be very familiar. And then stored procedures. Stored procedures are really thinking about executing a Python script in that runtime. So rather than a user-defined function, which you call or invoke by passing data to it and receiving an output, the stored procedure is just a script, right? If you had a .py script that you typically run on your laptop or a VM, you can just package that up as a stored procedure, throw it up to Snowflake, and execute it on our compute resources instead. And we'll talk about how to kind of structure that execution here in just a minute. Within the user-defined function category, there's a couple of different flavors, which we'll get into in more detail as well. But conceptually, they're really still the same kind of custom calculation concept. So let's take a look at what that mental model is. Frankly, as we've onboarded new people to my team, actually, over the last year or so, the formulation and getting comfortable with this mental model has probably been like the most important thing to enable for new employees on our team to then go out and help customers do this as well. So I think, like, for me, an objective or goal in this session is to hopefully you walk out of here with a better or your own sort of mental model about how to think about Snowpark. This is the one I like to use to really kind of distill it down to its simplest form. If you're transforming data in Snowflake in a SQL-like way or a data frame, sort of way, you have columns and rows, and you're just doing kind of standard SQL type transformations against those. That's the client API. Transformation is the client API, the DataFrame API. If you're doing any sort of calculation against that data, non-standard custom calculation, that falls into one of those three categories of user-defined functions. We'll talk about how to decide which of those three it falls into, but that's really calculation. And then that automation component, the execution of the actual business logic or the logical flow of your script or program or whatever it may be, is where stored procedures come into play. There's some exceptions. The exceptions are predominantly centered around very specific machine learning AI stuff, so we won't get into that in a ton of detail. But that's generally, I think, the simplest mental model to work from. Transformation is the client API, calculations are some flavor of a user-defined function, and automation or execution is the stored procedures. So what does it actually look like in terms of where things execute? This is always the question that SQL and Spark users come with when we start talking about this. Is like, okay, when I'm running this, am I using the same virtual warehouse nodes? Like, how distributed are different things, so on and so forth. And I think if you're a Python developer, maybe less familiar with sort of distributed processing systems, this is another kind of useful diagram to have. Of course, with the client API, you don't have to actually run your source Python script or code in Snowflake. From any external Python client, you can have a script or a notebook or whatever it may be, using that client API to push down compute onto Snowflake virtual warehouse resources. When you do that, as I mentioned, because of the way we do the SQL translation, fundamentally, that's going to execute on a virtual warehouse, specified virtual warehouse on just our native Snowflake SQL execution engine, right? From that same script, at the time that you two pandas or collect something, that's the moment at which you've pulled data out of Snowflake and you're now processing it in memory in that Python client. You'll see one of our 10 commandments around performance here is basically don't two pandas anything unless you absolutely have to. Selfishly, we don't want you to do that because if you two pandas something, we start making less money, but also you're probably going to have a bad time because now we're talking about taking whatever large scale processing you were trying to do in Snowflake, extracting that data volume out and processing it potentially in a far more constrained sort of environment. Within that, you might also do database object creation for the corresponding store procedures, UDTFs, and so on and so forth. Now, when we talk about the execution environment for user-defined functions and stored procedures, this is where, again, on the Snowflake virtual warehouse, on our internal compute resources, we spin up a Snowpark Python runtime that is then replicated across all of the various compute nodes that comprise that virtual warehouse. Now, if you take that same Python script that you were running outside of Snowflake, just using the DataFrame API before, and maybe you were calling user-defined functions, and you drop that into a Python stored procedure, the actual stored procedure script is going to run on our compute resources in this Python runtime. Importantly, the stored procedure code itself executes in a single node, non-distributed Python kernel. So just on one of the compute nodes, it can use more than one thread on the compute node. Part of the value prop of Snowflake is you don't have to worry about the compute. You just pick a size and it's all good. So we try not to talk about the threads too much, but for the hardcore Python developers, this is potentially important. You have access to the whole compute node, but it's still just running a single node. And that's why it's important when we start talking about large-scale data transformation, you have to leverage these other components inside of your stored procedure to get the scalable distributed execution that's actually doing the work, right? So the stored procedure is a Python script. It runs in a single node Python kernel on one of the compute nodes. Now within that, however, you may be making DataFrame API calls. You might be referencing other user-defined functions that you call, and those pieces that actually do the heavy lifting and are doing the work will get fully distributed and parallelized out across all of the compute resources available to the warehouse that the stored procedure session is using. The exception, of course, is still that two pandas. Two pandas is like so enticing. If you've worked in the pandas world all the time, you're like, man, if I just two pandas this, like I know exactly what I would do to it. But the same way that if you do that from an external Python client and you pull the data out of Snowflake, even in that stored procedure, if you run a two pandas type operation, you're not pulling it out of Snowflake per se, but you are basically isolating all the data onto a single compute node in memory, which starts to become a problem potentially for, large data. Again, with the exception of some very specific use cases for which we built Snowpark optimized warehouses that have larger RAM capacity compared to standard ones, where you might need to actually do something like that in a non-distributed way. But even though the data is not leaving Snowflake, you're probably going to have a bad time if you two pandas that work because you're no longer getting the benefit of the total pool of compute resources that are available to you through the virtual warehouse. Let's dive into some of these usage contexts just a little bit more. As at this point, I'm sure everyone's basically familiar with this data frame structure, right? You worked with some form of a data frame through either Pandas or Spark data frames or RDDs or Dask, and now, of course, Snowpark. And if you haven't worked with data frames specifically and you're a SQL person, like we're just talking about tables here, right? That's all it really is. Two-dimensional structures with rows and columns, features in the data that have definitions on the objects, as well as then transformations against the data that they contain. Snowpark data frames specifically, it's worth noting, are really just pointers to either tables or SQL transforms on those tables. So when we're talking about using the DataFrame API inside of a stored procedure, for example, that DataFrame object in your Python runtime is a Python object that really is just a pointer to a set of tables or queries, transformations that are on the Snowflake virtual warehouse. There's no actual like data within that data structure, if that makes sense. It's purely just a pointer to those operations. You can, of course, run kind of select style transforms out of that to pull data. You can run writes to do create tables and so on and so forth. But it maps very, very well to corresponding SQL. So even though syntactically it's different, and again, this is where if you're talking about the DataFrame API, it's going to look and feel a lot like the PySpark DataFrame API. You can basically map anything. I mean, you literally can map anything you're doing through the DataFrame API to a corresponding SQL statement. So when we talk about selecting certain fields out of a data frame, my favorite, just to select star from a table or something like that, doing filter type operations, group by, aggregations, creating new columns, doing window functions, doing merge statements and delete statements, and so on and so forth. Any of those standard Snowflake table type operations that you would normally do, you have Snowpark DataFrame corresponding either native Python methods that translate to those, or you always have the ability to basically call any built-in SQL function in Snowflake. Anything you can do in SQL, you can do using the Snowpark DataFrame API, and there's zero performance difference between the two. None whatsoever. They execute the exact same way. Importantly, the Snowpark data frames are very, very different from Pandas data frames, which a lot of the Python developers in the room are going to be very, very accustomed to working with. Whereas we have these Python pointers to SQL objects in Snowpark data frames, in Pandas data frames, we have in-memory data structures that are tabular in nature, similar to a data frame, but contained in memory, right? The computations associated with those Pandas data frames all happen within the Python kernel where that Python object exists. It's no longer distributing out to a larger set of compute resources. And by default, Pandas data frames only really exist in a single node capacity. Now, there's some exceptions. There are frameworks like Dask and Ray that help distribute Pandas type objects and operations, but that is worth noting. One of the things I think is, I don't know, I've observed it as interesting. Maybe that's like the nicest way to put it, is the prevalence of like Pandas in Python education is really fascinating to me, because a lot of what you can do in Pandas in terms of like index-based lookups and changes to the in-memory data structure and things like that, they're really helpful because they make a lot of intuitive sense, right? If you're learning Python and working with tabular structures, like you have this notion of like, I just want to change the value of this row in this column in this thing, so I'm going to use these indices to figure out where that is and update it and so on and so forth. There's a lot of bad habits that get built through that education though, when you start talking about now trying to do work at large scale. And I don't quite know who to blame. I'm always thinking about who to blame for this, but there's a lot of, when we start talking about like moving and migrating from that pure Python world into Snowpark, there's a lot of kind of behaviors to unlearn potentially, largely just due to things that like you don't, when you're working in Pandas, you're often working at a small enough scale that you don't really have to worry about them. They start to become a problem at large scale though. Store procedures, we've harped on this, so I won't spend too much time here. These are Python scripts that execute in Snowflake as Python code. I would almost think of this as just publishing a Python script and invoking it on like a EC2 VM, right? That's like basically what you're doing here. The difference is that EC2 VM is one of our compute nodes in your virtual warehouse. But that's fundamentally what it is. And then whatever you do inside of that, if you're using the Snowpark APIs, you're farming that out to other compute resources in Snowflake. If you collect or two pandas that data, you're now processing it in memory on that compute node instead. The easiest way that we've seen customers get started with Snowpark is they take their Python script that already maybe works with data in Snowflake in some way, and they say, cool, we're just going to wrap this up and drop it in as a Python stored procedure, and now we're using Snowpark. You got a guilty party up front here, okay? it works. It'll work. Like it's not gonna break, but you're gonna have a bad time again because you're basically at that point running that script like it's equivalent to running it on your laptop, right? The power of Snowflake compute is that you don't just have a laptop, you got like a whole bunch of laptops all processing the same thing. But we see this a lot where someone's like, oh, I want to just run this in Snowflake. Let me just drop my script into a stored procedure. Boom, it's going to work. Most likely. Not always, but probably. The problem is you're not really actually getting any benefit from that. So the real question becomes then how do I re-architect instead stored procedures or components of that stored procedure as other Snowpark concepts like user-defined functions that are going to let me leverage the entirety of what Snowflake and Snowpark offers me. I always, again, think of it as anything that's doing work on the data. That's not just saying like, run this, then run that. If this, then do this other thing. Anything that's actually doing the work, we need to figure out when we're talking about moving an existing application or starting from scratch, how do I best implement that using one of these other concepts? Oftentimes, for again, those Panda-centric workloads already that exist, that comes in the form of the DataFrame API, figuring out just what the corresponding methods and so on and so forth are. Other times it can be taking custom processing and architecting that instead as a user-defined function or UDTF. But that's what starts to leverage the full power of Snowflake compute for your Python workloads. The one thing that I would mention here, a key difference as well, we see this sometimes where folks want to, inside of user-defined functions, like execute queries, which is an interesting concept to say the least, but kind of gets you into a weird spot. Essentially, we don't allow that, right? So user-defined functions are taking data in, they're processing it, and they're presenting an output. Within that, you can't go query something out of a table or execute something else. The stored procedure is that mechanism. If we're talking about executing queries, the stored procedure is really that. And you need to figure out how to pass input for whatever you need to do into your user-defined function instead. Some exception here where we don't allow access to the database, but now through dynamic file access, you can pass in things like S3 URIs and then directly load files into the inside of the UDF, do some things like that. But you can't like run SQL statements or something like that. Okay, UDFs. Again, vanilla UDFs are one-to-one row-wise calculations. We do all of the parallelization of that execution across the virtual warehouse compute nodes for you, but they allow you to implement custom Python logic to do one-to-one style transforms. When performance is a concern, if there's a native DataFrame API or SQL operator that allows you to achieve the same thing you're trying to do, you will get better performance using the SQL or DataFrame implementation instead. The reason for that is, again, when we actually execute these Python UDFs across the worker node within the Python sandbox, we're basically spinning up a bunch of independent Python processes. We load that bytecode into that Python process, and then Snowflake handles the passing, random batching, and sending of data to all these independent processes for you, right? So they independently churn on data, produce results, Snowflake kind of distributes and then aggregates the results back for you. But at a certain point, once the data's in there and the code's loaded, it's just Python code running. And as much as we all love Python, it is not the fastest, most performant language, right? Being interpreted and everything else, it just is like, it's just not. And so by introducing Python UDFs for things you could otherwise do with SQL or the DataFrame API, you're just inherently going to get worse performance because you're getting the same scalability. Like you have to do the same amount of work. You get the same parallelism associated with that data. It's just like, do you want an interpreted language doing it or something else doing it that's going to be faster? That's like basically the trade-off that it comes down to. This just walks through that in a little bit more detail. The vectorized Python UDFs extend those same vanilla Python UDFs to be more performant by at least letting you take advantage of some of the internal optimizations that have been made in Python to operate on vector objects versus row by row. So vanilla Python UDFs, as we randomly distribute all those row sets to these independent Python processes, we basically then just like loop through the rows. Like this row gets processed, cool. Then the other one goes, and we just loop through. We do that a bunch of times for you. But that's effectively what we're doing. Instead, a lot of things in Python, a lot of libraries, a lot of functionality has been optimized to operate on things like NumPy arrays or underlying vectorized structures. What the vectorized or batch API lets you do is take that same function and apply the vectorized version of that functionality. And Snowflake, rather than doing row by row style execution, basically randomly batches that data as a vector object, passes it into the Python interpreter, and then you get the corresponding Python execution. So whereas before we had Python performance compared to SQL performance, instead now we're getting vectorized Python compared to pure Python performance here. So we're somewhere in the middle. Again, the pure SQL operation is always going to perform better than the vectorized UDF, which is going to perform better than the vanilla UDF. But in general, if you're writing a Python UDF, just use the vectorized API. Unless for some reason, whatever you're trying to accomplish just cannot be implemented in a vectorized fashion, you're just wasting some performance gains to be had if you don't use it. It involves a lot of internal optimizations too in terms of how we create the vector structures. But then of course, again, the important thing is that you get better just pure Python performance as a result. So you can see here largely in terms of how the sandbox and the interpreters get spun up, it's the same. The difference is now from the worker thread outside of the Python process to the Python process, we're instead taking a whole batch of rows, converting that to a data frame or vector structure, calling whatever handler we have for that function, and then converting from that series using things like arrow back out to the output batch of rows, which then is ultimately what's returned to you. UDTFs, my favorite, the most confusing, but also the coolest, because you can basically do whatever you want with these things. UDFs are one-to-one, and a lot of things that we need to do are not one-to-one, right? We have many-to-many, many-to-one, one-to-many, one-to-one style operations that require some sort of statefulness, where if I need to know what I did on the previous rows in order to do what I'm trying to do on the current row, user-defined functions by themselves do not support that. UDTFs, however, do. UDTFs are perfect for doing any kind of logical partition-based processing of the data. So the example I always like to give is if you've got data for thousands of stores in a table, right? And you're just trying to do, for each of those stores, you're trying to do some processing associated with that data, right? Whatever it might be. It could be just like aggregating or finding a minimum value, whatever it might be. Store 1 doesn't need to know what store 10 was doing in order to do the store 1 calculation, right? So your UDTF, you define your process and end partition methods to take for a single store, what processing do I want to do? The process method within a UDTF definition says for each row, what do I do? And then the end partition method says, okay, once I've processed all the rows, now what do I do, right? That's essentially what you're defining. You write that code to process a single batch of data. Then when you invoke the UDTF, we use the partition by clause to specify the field in the table that's being passed into the UDTF that defines those logical partitions. So if you're doing, my custom UDTF over every store ID in your table, you simply call my UDTF, you pass in the input columns, and you say, all right, partition this by store ID. And what that does is Snowflake, then the same way that we have those parallel independent processes for Python UDFs, we do that same thing, but the difference is rather than passing random batches of data, we pass all of the store 1 data to the same thread. We then pass all of the store 2 data to the same thread, and so on and so forth, which allows you this flexibility to do very, very custom stateful processing, as well as the ability to return different, like with the UDF, if you pass in 100 rows, you get 100 rows out. With the UDTF, you can do whatever you want. You can return nothing, right? I mean, you return a whole bunch of stuff. It doesn't matter. You at each stage throughout the process and partition method, you yield some sort of result or you don't, and it has nothing to do with the input rows. It's just pure processing of that logical partitioning of data. The important thing there is that you still get full parallelism across these store IDs. Every store ID is processed independently in parallel, but within a single store, you're basically getting the same kind of single node execution, right? You're basically just churning through each store in many, many different ways. Talk through most of that. So let's look at an example. If you wanted to do something like a forecast error calculation for maybe all these stores. Maybe you produce sales forecasts, quarterly sales forecasts for all your stores, and now you want to go through and calculate what was my error, and I want to see error by store. Within our UDTF, we basically need to compare how are my actual values compared to my predicted values. All I really am doing then for each of those rows that I'm getting, all right, this is the actual value, this was the predicted value, and I'm not even returning anything. But I just gather up these row sets, and then when I get to the end of the partition, I've got some handy Python libraries and modules that do automatic error metric type calculation for me. I just call those against my actuals and predictions, and then I return that tuple of metrics. Now, when I call this UDTF, I simply say, calculate forecast error on my input predicted and actual values, partition it by store ID, and boom, I have for every single store ID what was my RMSE, my MA, my bias from my previous forecast, all executed in parallel across all the compute resources available to the underlying virtual warehouse. So with those usage contexts in mind, how would you actually construct this in like a real world workflow? How would you map what you're building to these different concepts? I always like this example. This is actually from a customer that I work with out in Denver who takes call center transcripts. They clean and reformat those transcripts to get tighter, cleaner sentence objects and things like that. They then go through segment and tokenize the underlying raw text. They run then a sentiment classification model against that, and then have some aggregates by demographic and location, things like that, that they ultimately produce and serve out to a dashboard to see how their call centers are performing. Are they having good or bad experiences more oftenly in certain locations for certain populations of customers and so on and so forth. The way they did this before, they had a bunch of cloud VMs in a cloud provider. They loaded the raw transcripts into a Snowflake table, and then they had another job that would kick off and it would query all those raw transcripts out of Snowflake, do the cleaning and reformatting, and then dump that data back into Snowflake. And that would kick off the next bit, which pull all those results out, do the segmentation, the tokenization. They write those tokens and those segments back into Snowflake and kick off the next, and that thing would pull that out, right? So you start to see where one, seems like a lot of unnecessary pushing and pulling of data on the one hand, and two, there's a lot of work around orchestrating and managing those VMs, issues with the scalability and performance of the Python runtime there. There's all kinds of problems you can start to introduce. So instead, we said, all right, let's do this whole thing in Snowflake. We'll use Snowpark Python. We talked through kind of like how would you design this sort of code structure. So loading raw transcript text into Snowflake tables is very straightforward to do through using the DataFrame API, right? You have .write operations, you just take data, dump it into a table. Cleaning up HTML type tags and things like that, and just weird like sentence breaks and all kinds of nonsense from this raw text data. Very straightforward to do using like regex style functions and a number of other things. So we actually use just common built-in SQL functions through the DataFrame API for that bit as well. Now the segmentation and tokenization of the underlying text is not easy to do in SQL. I never like to say it is impossible to do in SQL because in theory, like it's code, you can do anything, but very, very difficult to do, very, very easy to do in Python. So in this case, because we had a bunch of rows of text data, we need to produce a bunch of rows out of tokens and things like that. We built a vectorized UDF that used some common Python open source libraries, took in that raw text, produced the tokens. That's all there was to it, right? Pretty straightforward. Once we had those tokens, we could then actually run our sentiment classification model against that to determine whether this was a positive or negative experience on the call, using a machine learning model as well. Both of those are implemented as vectorized UDFs, because in our case, they have vectorized implementations associated with the work you're doing. And then to do that summarization, we built a single UDTF that did all the aggregate calculations for them, but gave them the flexibility then to alter the different categorical variables by which they produced their analysis. So one user-defined table function that took in these inputs and calculated these aggregate metrics and statistics. And then they could decide if I wanted to just break that down by gender or age category, when they call the UDTF in the context of a query, they specify exactly that. And if they then wanted to do it by age and gender and state or whatever, location data they would have, they could use the exact same UDTF and just change how they were calling it to get this same parallelized execution. Those were all the bits that are doing the actual work on the data, right? DataFrame API calls, vectorized user-defined functions, and UDTFs. Now we needed to package this up so that they could actually run it in Snowflake too, which we did through combining a couple of these steps into independent stored procedures. Those are the scripts that say, run these DataFrame calls, and then call this UDF, and then call this UDTF, right? Simple scripts. They're very lightweight. They don't do any work themselves. They just farm out commands to do other stuff. We have those run in sequence, orchestrated as tasks, all bundled up into one directed acyclic graph, which then runs on a daily basis for this particular workload. That notion of separating the workflow and automation and orchestration from the stuff that's actually doing the work continues to be, I think, the hardest or the biggest challenge customers I work with struggle with as they start looking at Snowpark Python. It all comes down to working and figuring out how to best operate within this particular mental model. On the DevOps side, and I'll just touch on this briefly because I do want to go through my performance considerations. The really challenging thing with Snowpark Python largely has to do with like why DevOps for databases is hard. My colleague Jeremiah Hansen has done talks at Summit in the past and written a lot of articles around effective DevOps for databases. The thing that gets hard about Snowpark is that those user-defined functions and stored procedures now exist as database objects, right? But they also exist as code and source code in like Git repositories and things like that. And for software engineers who have just worked in like Python development land, right, and haven't had to do kind of database ops before, this is like a whole new sort of concept. And so there's challenges associated with managing stored procedures, the code for stored procedures that are largely just using the DataFrame API. That's pretty straightforward. That source code lives in Git or wherever. And then really all you're doing is instead of deploying to, doing standard like script deployment kind of processes through CI/CD, you're just creating like your deploy mechanism is now like create stored procedure from this file, right? It's like not fundamentally all that different. But when you're really highly dependent on user-defined functions, which themselves are defined through code and also exist as database objects, and so you're trying to marry up versioning between these two things, it starts to get a little bit tricky. Largely, what I see a lot of customers doing is implementing actually temporary UDF creation as part of this, so that UDFs aren't actually persisted in database. They have them created temporarily as a session object when the script executes. So it runs whatever version it has in its source code at that time, processes the data, and then when the session closes, the UDF, poof, it's gone. It's not permanently deployed as a user-defined function. The other common approach I see is that when pushes to main happen in their source code, they just like redeploy it all, which terrifies me because all of a sudden you start breaking stuff that you didn't know you were going to break. So I see more and more customers are actually using temporary object creation as the mechanism to sort of deal with this. It lets them really focus on CI/CD and DevOps for code and largely eliminate the need for sort of database ops for these specific workflows, except of course in the same way that you always have to think about like how my source data might change in any sort of application that interacts with a database. I'm going to skip through the MLOps stuff here for the sake of time. The first rule of Snowpark, I always remind people on the performance side of things, is that traditional Snowflake performance principles always apply. If your data has high skew and it's clustered poorly, you're going to have a bad time, whether you're using Snowpark or SQL or anything else, right? Warehouse sizing, according to the partitioning in your data and things like that, is still important, whether you're talking about SQL or Python code. And if you really want to get into all those traditional Snowflake performance principles, you can call my colleague Darren Gardner, who's far smarter than I am on this particular topic. But when it comes to Snowpark specifically, the number one rule is don't egress the data. The second that you egress the data, you're going to have problems in the sense that you're now constrained in terms of resources in a way that you weren't before. The second is use data frames first because you get native Snowflake performance and execution through that. The third, anything that manipulates, computes, analyzes, transforms the data, implement as UDFs so you get parallelized performance and scalability. Don't do the processing in the stored procedures. Farm the work out to other stuff as much as possible. And don't do pandas anything unless you have to sometimes. The other thing is that if you write bad Python code, it's going to be bad in Snowpark too. That really has nothing to do with Snowpark. It drives me nuts when customers say, hey, Snowpark stinks. My code's not working. And I look at their code, I say, well, don't take this personally, but I think Snowpark's not the problem here. The next is that when you're thinking about designing for Snowpark, really assess and map how would my existing objects fit as Snowpark concepts. Do they already map well? Have I written kind of functional code in such a way that I can just now say, okay, great, this function is just a UDF, same as before, it's got data in, data out, no big deal? Or do you need to re-architect to better leverage those components? The other thing is to basically pull reusable stuff out of main logic. The reason being that a lot of Snowpark Python code like re-executes as batches of data get processed through it. And so rather than like have certain things like happen over and over and over again that you just need once, you just do that at the top, right? Vectorize whenever possible. I already talked a lot about that. And the last one is leverage Python caching on top of the Snowflake caching. There's a lot of layers of caching within the Snowflake architecture, from the data itself to the packages in the runtime to the data on disk, to the query results, and so on and so forth. But internally in the Snowpark Python code, something you also can think about is maybe I can cache loading of certain reference data and artifacts as well, rather than reading from disk repeatedly, right? Just throw cache tools around your load artifact function and boom, you load it once at the beginning, and then you're basically reducing a lot of overhead. So with that, hopefully this has been informative in how you think about Snowpark Python. When these recordings go out, we'll also make sure to include some links to a couple blog posts that go into these topics in a lot of detail. Thank you so much for attending. Thank you for being at Summit. Have a great rest of the week.